So let's look at treatment chambers in detail. But before that, let's uh, let's cover some basic aspects of the treatment chambers. So in a Stenter, we have multiple treatment chambers, and the usual number of treatment chambers is between 6 and 10. However, we can have more than 10 treatment chambers very easily. Each treatment chamber usually has a cloth capacity of approximately 3 meters, but then again, modern designs and manufacturers always aim to increase the cloth content in individual treatment chambers. So we can have treatment chambers which accommodate up to 3.5 meter length of fabric at a time. It is very important to understand and note here that the machine speed, that is the speed at which the Stenter can be run, is directly dependent on the number of treatment chambers. So if you have more treatment chambers, then you can run the Stenter at a higher speed. Let's look at the parts that are provided internally in a Stenter treatment chamber. We are first going to look at the parts with the help of this actual cross section of a treatment chamber. And then in the next slide, we are going to talk about the parts again with the help of a schematic. So on one side of the treatment chamber, a heating system is provided, for example, a gas burner. We will talk more about it. There is this large chamber type thing in which the process medium, for instance, air, is heated up with the help of the heating system. Then we have circulation fans which draw the heated air from the heating chamber and pass it on to a set of ducts. We have a lower duct and we have an upper duct, and the fabric is sandwiched in between the upper duct and the lower duct. So in most cases, the process medium, that is, for instance, hot air, is blown on either side of the fabric. We also have lint filters that play an important role, as we will discuss later on. Let's look at the parts again, now with the help of a schematic diagram. So here is a schematic diagram of the cross section of the treatment chamber. Once again, in the lower section we have a heating system. We have the heating chamber where the process medium gets heated up with the help of heating system. Circulation fans that draw the heated air and pass it on to a set of circulation ducts, and lint screens. And an additional component which I did not mention in the previous slide is the exhaust system. So to maintain the efficiency of the process, a certain amount of the process medium has to be sent to the exhaust. The first system that we need to consider is the heating system, and this is because in the treatment chambers in a Stenter, the process medium, which is usually air, is heated up, and that in turn heats the fabric, and the processing conditions that are required are maintained with the help of various types of heating systems. So in this slide, we are just going to first talk about a list of different heating systems, and then in the following slides we will talk about the different heating systems in detail separately. So the first one is direct gas heating. We can have thermic oil heating. Steam can also be used to heat the process medium in a Stenter treatment chamber. We can have basic electric heating, a combination of electric and steam heating, and even hot water. However, it is very important to note that the first two heating systems, that is the direct gas heating and the thermic oil heating systems, are the most common heating systems that are used on a Stenter. Let's now see how the direct gas heating system works. Once again, this is arguably the most common form of heating system that is used in a Stenter. So in direct gas heating, natural gas is burned directly inside the treatment chamber, and this is done with the help of massive gas burners that are provided inside the treatment chamber. The combustion gases that are produced by these huge burners are circulated directly in the chamber, and here it is important to note that in direct gas heating system, the combustion gases directly come in contact with the fabric. So if the combustion of natural gas, that is the fuel, is not proper, then that can lead to all sorts of problems. Let's now look at the second most common heating system that is used in Stenter treatment chambers. This system is known as thermic oil heating. And this system is relatively more common in parts of the world where natural gas is either too expensive to be used as a fuel or it's unavailable altogether. In this system, instead of a gas burner, a heat exchanger is used to heat the air inside the treatment chamber. So, in exactly the same location where we would provide a gas burner in direct gas heating, we will provide a heat exchanger, as you can see over here, in thermic oil heating. And in this heat exchanger, we pump in hot thermic oil and it passes through the heat exchanger, and as it exchanges heat with the air inside the treatment chamber, its temperature is dropped, and so the cold thermic oil, or the oil which has decreased temperature now, is taken out of the other side of the heat exchanger. Now the air inside the treatment chamber is passed through this heat exchanger continuously, and in this process it takes up heat from the hot thermic oil and gets heated up. The rest of the working of the system is the same. So as you can see on the right hand side, the lower right hand side of the schematic that is shown here as shown in yellow, the circulation fans draw this heated air and pass it to a set of upper and lower ducts. The fabric, as always, is sandwiched in between the upper and lower duct.
Okay, so obviously we can compare the two systems, the two most widely used systems, that is the direct gas heating and the thermic oil heating systems. So if we talk about the features of direct gas heating system, then of course the first point to mention is that this system has highest efficiency. Efficiency in a sense that as soon as the burners are fired, the air inside the treatment chamber starts to heat up almost instantly. So in that sense, these have maximum efficiency. Um, However, if the natural gas is not burned properly, then there can be ash or some unburned fuel which can cause problems once this comes in contact with the fabric. So here, the working of the burners it becomes very critical. Okay, as obviously well, this point is related to, in a way, it's related to the first point also. In direct gas heating system, the heating up time is very short, right? Or in other words, if you compare it with all other heating systems, then this has the shortest heating up time. Again, because of the fact that as soon as the burners are fired on, the air inside the treatment chambers starts to heat up. Low maintenance is required. Well, that's debatable in a sense that there are no heat exchangers. Heat exchangers require some specific maintenance protocols. However, in this case, we have these burners, and these are like complex electronically controlled burners. Things can go wrong with these burners. So if we exclude the burners from the discussion for a while, then we can say that direct gas heating system has low maintenance because there are no heat exchangers inside the treatment chambers. Less space requirement compared to thermic oil heating because, as mentioned in the previous slide, in a thermic oil heating system, you need a separate oil boiler and then all that piping that is required to feed the oil to the Stenter and then take the oil back to the boiler from the Stenter. So in that sense, because there is no oil boiler present, it's just these burners that are installed in the treatment chambers. So you can say that less space is required. Now let's have a look at the features of thermic oil heating system. The main feature is that it provides uniformly heated circulation air because combustion gases are not directly present inside the treatment chamber. So there are no chances of any sporadic increase in the temperature of air from time to time. The air is passing through a heat exchanger, and it gets mixed up properly, and the heat exchange is of course relatively uniform. So the temperature of air at all times is very uniform in this system. Low emissions, that's again debatable. It's because if your thermic oil boiler is gas fired, that is, it uses natural gas to heat up the thermic oil, then um, probably you cannot say that the system has this characteristic low emission. But if your thermic oil boiler is, let's say, electric, then there is a possibility that the overall emissions of the system will be low. There is this minimum risk of yellowing effects on fabric. This occurs. This can occur potentially due to any unburned fuel or ash or any uncontrolled temperature spikes in the air. So all of this is not possible in thermic oil heating. There is no ash or unburned fuel that is present. Therefore, the risk of any unwanted effects on the fabric are minimal. And of course, there is a heat exchanger, so the heat exchanger would require its own maintenance. We have a thermic oil boiler, which is a complete machine on its own. So, of course, maintenance of this thermic oil boiler is one factor to be considered. One advantage of thermic oil heating system is that we can have different fuel options in it. So the thermic oil boiler can be gas fired or electric, as I mentioned before. This is not possible in case of direct gas heating system. Of course, direct gas heating system will always require natural gas as fuel.
Let's now look at air circulation one more time in a bit more detail, because then we will talk about why we need precise control over air circulation when we are processing a fabric in a Stenter. So, first of all, the heating system is activated. Let's consider the example of direct gas heating, in which case a natural gas burner is actually turned on in the heating chamber. As this natural gas burner produces combustion gases in the heating chamber, the air inside the chamber is heated up. This air is drawn in axially by centrifugal fans, which then blow this hot air into separate upper and lower ducts. As the fabric is placed in between these two ducts, air comes in contact on both sides of the fabric, and this is where heat exchange with the fabric takes place. So once this hot air has exchanged heat with the fabric, the temperature of this air drops, and this air with decreased temperature is circulated back into the heating chamber. A part of this air has to be sent to an exhaust, and this is inevitable because we cannot circulate 100% of volume of the air in the treatment chamber. There are reasons for that, because let's take the example of simple heat setting of fabric in the Stenter. In that case, the moisture content will increase inside the treatment chamber when air comes in contact with the fabric. And if it keeps building up, then the evaporation efficiency will be reduced. And that is why a part of the air volume that is in the treatment chamber has to be sent to exhaust, and an equal proportion of fresh air has to be taken into the treatment chamber. And this is sort of an ongoing cycle. So when we set the process conditions in a treatment chamber, we control the volume of exhaust gases, because that then determines the working efficiency of the Stenter, and that has a direct effect on the cost of our process as well. So if we are taking in a large volume of fresh air in every cycle, then that volume of air has to be brought to the right temperature, which means more energy consumption. So it has to be the right balance between the amount of air that we are recirculating back and the amount of air that we are sending to the exhaust.
Okay, so we have seen how air is circulated inside the treatment chamber. We have discussed that uniformity of air circulation is very crucial. This is to ensure that the fabric characteristics are uniform across the entire width and along the length of the fabric. And of course, we want to control the flow of air as well. That's the airflow volume, if you like, or airflow rate, if you like. We want to control it, because if the air is blown with too much pressure on a low GSM lightweight fabric, then this can cause excessive fluttering of the fabric. and this is not what we want, because excessive fluttering of the fabric can result in the fabric getting detached from the chains, or other damages to the fabric can be caused. So uh, if I summarize this, then we are talking about two important controls on the circulation of air. One is the uniformity of air circulation, that is, the air pressure should be same across the entire width and length of the fabric. And then the second aspect of this control is the airflow rate, on which is set according to the type of fabric that we are processing. So let's see how these two aspects are achieved with the help of different features of the air circulation control systems. The first thing to notice is that the upper duct and the lower duct that we have seen in the previous images are tapered. So these ducts are tapered to compensate for pressure drop across the width. Let's look at this with the help of a diagram. So that's the treatment chamber that we have been discussing about. And these are the tapered ducts in between which the fabric is placed at all times. So what we are talking about here is that as the air is blown by the fans into these ducts, it travels in this direction, and of course, as it travels, its its velocity decreases. But with the help of this taper, this is sort of a nozzle type arrangement. With the help of this taper in the ducts, the air velocity is maintained, and that is why tapered ducts are used. So this is one feature to ensure uniformity of air circulation across the entire width of the fabric. So because of this taper, as I've mentioned, the airflow rate at all points along the length of this duct remains the same. The second feature we have, which is provided to control the airflow rate or airflow volume, if you like, is that we have adjustable nozzles in these tapered ducts. So once again, let's have a look at what we are talking about exactly. So these are the tapered ducts, and they look something like this. So these tapered ducts have these nozzles or openings in them, and these openings are they look something like this. These openings are adjustable. We are talking about these nozzles here. So if you want to increase the airflow rate on the fabric, then these nozzles are fully opened. If you want to reduce the airflow rate, then it is possible to partially close these nozzles, and so the airflow rate is reduced. As I mentioned before, we want a reduced airflow rate for lighter qualities, or whenever there is a chance of excessive fluttering in the fabric. The third feature to maintain uniformity of air circulation is to have separate fans for the upper and lower ducts. Now, I've not used any image here of a Stenter in which there is only one circulation fan. But in older models, you will find in the industry that the upper and lower ducts were fed by a single fan, a single circulation fan. In that case, there is a pressure difference uh, in the air coming out from the upper and lower ducts. So to address that problem, in relatively newer models of Stenters, and when I say newer, I am talking about for the last, let's say, 15 or 20 years, or maybe even longer than that. So the manufacturers came up with this concept of having separate fan for the upper and lower duct. So in this case, there is no pressure difference in the air coming out from the two. So if you look at a Stenter from the outside, you can see for a single chamber, there are two fans. Actually, this, if I mark it, this part, this box that you see is one single treatment chamber. It's not two treatment chambers. The the lines that you see are actually representing the panels, but this is one single treatment chamber. So you can see two fan motors over here. this part. And from the inside, it of course looks like this. So we have one fan for the upper duct and another dedicated fan for the lower duct. And that's how we maintain very uniform pressure in both circulation ducts. There's a fourth feature that helps in ensuring uniform air circulation, and that is counter arrangement of chambers. You might have already noticed that the Stenter treatment chambers are identical in the structure. So whether we have 6 treatment chambers or we have 11 or 12 treatment chambers, their structure is exactly the same. So the chambers are placed alternately, or what is called a counter arrangement. What I mean to say here is that if, let's say, this is the internal view of the first chamber, then you can see the the circulation fans are on the left hand side, while the burner is shown on the right hand side in yellow, as you can see on the other side, right? So let's say in the first chamber, the fans are on the left hand side and the burner is on the right hand side. So the next chamber, which will be identical in structure, will be placed will be flipped, and it will be placed like this. So now in the second chamber, the fans, the circulation fans are on the right hand side, and the burner or the heating arrangement is on the left hand side. That's the burner now on the left hand side. And this alternate or counter arrangement is followed for all the treatment chambers. This further ensures that if there is any variation in air circulation, despite all the measures that we have discussed before in the previous slides, still if there is any slightest variation in air circulation, then it is compensated for by this counter arrangement of the chambers. Because there is still a possibility, after all the features that we have discussed, the 3 features that we have discussed before this slide, there is still a slight chance that the air pressure on this side, with the side of the duct which is near the centrifugal fans, is slightly higher than the air pressure on this side. Now this is usually not expected, but the point here for you to understand is that despite all the features that are incorporated into the design of the stenters, to make sure that there is absolutely no variation in air circulation, there is still a slight chance of a slightly greater pressure of air on this side, the side which is near to the centrifugal fan, and slightly less pressure on this side, the side which is further away from the centrifugal fans. So to compensate for this variation, the chambers are placed alternately, as we have discussed in this slide. So now in the first chamber, this slightly high pressure is exerted on this side of the fabric, but then in the next chamber, it's the other side of the fabric which experiences slightly greater airflow. So this is how the variation is actually covered up, if there is any. I mean, we try to eliminate any possible variations in airflow, but just an additional feature is this one. Okay, then we need some controls that work in case of machine stoppages. So if for any reason there is an emergency stop, then of course a lot of fabric will be inside the treatment chambers. And in this case, in order to avoid the fabric from damage, or in order to unnecessarily change the characteristics of the fabric that is present inside the treatment chambers, we want a system that diverts the circulation air away from the fabric which is present inside the chambers. So there is a system which consists of dampers. The dampers are provided in the circulation ducts which divert away the air from the fabric. You will understand this in a much better way with the help of this diagram. So again, the treatment chamber, and in normal mode of operation, when the fabric is being processed, the circulation fans are constantly blowing air into the upper and lower ducts, as shown here with the help of these arrows. But if there is a sudden machine stoppage, we want to restrict this airflow immediately. So if there is a machine stoppage, then automated dampers close the entry part of these upper and lower circulation ducts. And as these dampers are closed, the air is diverted away from the fabric, as shown with the help of these arrows here. So these dampers are connected to motors actually, and then the machine controls detect that there is a sudden machine stoppage. Those motors are turned on automatically, and the dampers are closed, thus diverting away any air from the fabric. Okay, it's a lengthy description. Let's summarize this aspect of the treatment chambers, the control of air circulation. So we have discussed that a number of features of the air circulation system inside a treatment chamber ensure uniform and controlled air circulation. I think there is a typing mistake over here. It should not be circulations. Circulation is good enough, I think. Okay, so what are those features? The first one that we discussed is that we have tapered ducts. Tapered ducts are designed to compensate for any velocity drop. As the air travels from one end of the duct to the other end, its velocity can drop if the ducts are not tapered, right? So this profile of the ducts ensures that this will not happen, and so the air velocity is maintained. Then we have adjustable nozzles in the duct. We can change the opening of the nozzles, the size of the opening in the nozzles, to adjust the volume of air that is blown onto the fabric. This point is related to the fluttering of fabric. The third feature that we have discussed in this air circulation control system is that we have separate circulation fans nowadays for the upper and lower circulation ducts. If we use a single fan, then we would expect that the air pressure would be slightly higher in the lower circulation duct and relatively lower in the upper circulation duct, just because the air will have to travel a longer distance. So to avoid this problem, a dedicated fan for each duct is used nowadays. We have a fourth arrangement, which is the counter or alternate arrangement of the treatment chambers. So in one treatment chamber, if the burner is on left hand side, then in the next treatment chamber, the burner will be on the right hand side, and so on. This continues for all the treatment chambers. And then we have these bypass passages, the last point that we discussed, to divert away air from the fabric in case of machine stoppages. Bypass passages and dampers, right, that we have discussed in the previous slide.
So that was all about how we control air circulation and why do we need very precise control on the amount of air that is circulated and how it is achieved. The image that you see in this slide is just simply showing the insulation that is provided in the walls of the treatment chambers. You probably have already noticed that the whole process is very energy intensive. We are heating up large volumes of air in the machine, and therefore, to make the machine more energy efficient, manufacturers these days they do their best, and they try different things, and they have different systems and different options in the machine. So one of the very basic things that is done in the design of the treatment chambers is to insulate the walls, and it's supposed to be a very good thermal insulation, usually up to a few inches, that prevent loss of heat from the treatment chamber.
Okay, one of the parts that we discussed before very briefly is the lint screens. Now, as I briefly mentioned before, usually in case of heat setting, we treat the fabric with hot air only. And in case of textile fabrics, usually a lot of lint is generated from the surface, especially when the fabric is subjected to hot and dry air. So this lint or this fluff is added into the air inside the treatment chamber, and therefore it needs to be filtered out. For this, we use the lint screens. This is although it's a simple filter, however, it's very important for the efficient working of the machine, and to prevent any fire. If the filters are choked up, if the lint screens are choked up with fluff, then the airflow through through the lint screen uh, will not be proper, and therefore the efficiency of the machine will decrease. Similarly, if the lint screens are not properly removing the lint, then there is a chance that if it builds up in the air, then it can catch fire, of course. So these lint screens are simple filters that are usually cleaned by the operators manually. Some manufacturers introduced automatic lint screen cleaning systems. However, I mean, it's just a fancy thing in my opinion. So from the outside of the treatment chambers, you can see these sort of trays or filters that can be drawn out or extracted, and the workers manually clean the filters from the lint. Now, what should be the frequency of cleaning of these lint screens? Well, that again depends on the fabric that you are processing. Usually, for a normal woven fabric, let's say you might require cleaning after every 2 or 3 days, or maybe even before that if the fabric that you are processing creates a lot of lint. So the operators, it's one of the jobs that the operators have to do all the time, that they inspect the lint screens frequently and clean them as and when required.
After the fabric leaves the treatment chambers, it is passed through a small cooling zone. The the reason that we need a cooling zone is because the fabric leaves the treatment chambers at a very high temperature, and before the fabric is stored in a batcher, or if it's plated in a trolley, the fabric temperature has to be lowered. This is required to lock the processing conditions on the fabric. So whatever treatment you have carried out, you have to bring the fabric below that temperature so that its characteristics are locked. And this can be simply done by blowing ambient air on the fabric. That sort of cooling system or cooling zone is just called air cooling system. There is another system that is used in cooling zone. Some manufacturers prefer this one, and in this system, the fabric that leaves the treatment chambers is run in contact with these large water cooled drums. The purpose and the objectives of the cooling zone remain the same, and that is to lock the fabric characteristics after the treatment is done.
So what are the key process controls as far as the energy conservation in a Stenter is concerned? Before that, you first need to realize that how significant is this heating process in terms of energy consumption in a Stenter. So this heating up of air can consume up to 60% of the total energy that you require to run a Stenter. So uh, that's why we are very careful about controlling the exhaust as well. So key parameters to monitor and control if you want to conserve energy are: number one, the exhaust humidity, the fabric temperature, and the residual moisture in the fabric. So in a standard treatment chamber, the exhaust humidity sensor is of course placed at the exhaust ducts. The fabric temperature sensors are provided inside the treatment chambers. Usually these sensors are non-contact sensors. So they can read the fabric temperature without making any physical contact with the fabric. And then we have the residual moisture measurement systems, some sensors which can measure and record the moisture coming in the moisture in the fabric which is coming out of the treatment chambers. So these three controls together uh, are monitored to ensure that the Stenter is working efficiently and we are able to conserve as much energy as possible. Let's discuss these. As far as the exhaust humidity is concerned, I have already mentioned that if you are heat setting a fabric, you might have just soak that fabric in water, and now in the treatment chambers, of course, the water is being evaporated off. So humidity or the moisture content in the process air is increased. However, we monitor the humidity in the air which is sent to the exhaust, and as a thumb rule, you can say that the exhaust humidity should be between zero point 0.1 to 0.15 kilogram of water per kilogram of air that is coming out of the exhaust. If the exhaust humidity is less than this, if the exhaust humidity is less than zero point 0.1 kilogram of water per kilogram of air, then this means that your exhaust volume is too great, which means you're sending a larger volume of circulated air to the exhaust, and therefore this would indicate that you can adjust the dampers in the exhaust and reduce the volume of air that is coming out of the exhaust. However, on the other hand, when we are processing some synthetic fabrics, sometimes it is required that the exhaust is fully open. I mean, that's a process requirement. We cannot restrict the volume of exhaust air in processing of some synthetics. So the exhaust humidity is of course monitored with the help of sensors that are placed in the exhaust ducts, and these sensors are connected with machine controls that indicate if the exhaust volume is too great. The second key process control that we have listed down is the fabric temperature. Careful monitoring of fabric temperature is required to control the dwell time. Now, I've been using this term for a while because I'm assuming that you are well aware of the heat setting process. Uh, Probably you have studied heat setting in detail in your textile dyeing course. However, if it is not the case, then you can let me know, and I will prepare a short video regarding heat setting as well. So dwell time refers to, let's say if you want to heat set polyester, then you will be required to uh, raise the temperature of polyester to, let's say, 200 degrees centigrade, and then maintain that temperature for, let's say, 10 seconds. That 10-second duration which is required to properly heat set the polyester fabric is the dwell time. So fabric temperature needs to be monitored very carefully to control the dwell time. We need to know exactly when the fabric reached the desired heat setting temperature inside the treatment chamber. And then we can calculate the dwell time and then subsequently adjust the speed of the machine. If the fabric is getting more dwell time than what is required, then we can increase the machine speed of the stenter. If the fabric is getting less dwell time than what is required, then we have to reduce the speed of the stenter so that the fabric spends a longer duration inside the treatment chambers. And of course, a careful monitoring of fabric temperature is required to ensure that the fabric is not what you can say overdone. So for instance, if a fabric has to be kept at 200 degrees centigrade for a certain time, then we should know that whether the fabric temperature is 200 or less than that or more than that. So normally in modern machines, again, these systems are automatic. So fabric sensors, which look something like this. As I mentioned, these are non-contact sensors. They detect or measure the fabric temperature without any physical contact with the fabric. These sensors are, of course, connected to the machine controls. In modern machines, if these sensors detect that fabric temperature is less than what you want it to be, then the machine controls will automatically increase the the burner output or make necessary adjustments to increase the fabric temperature. And the third aspect is the residual moisture. That is the moisture in the fabric which is coming out of the treatment chambers. Now, we want the fabric to be dry when it comes out of the treatment chambers, but if it's bone dry, then that might not be required actually. So if we have a system, we can have sensors that are installed at the exit of the treatment chambers. Usually these are contact-based sensors, and they measure the moisture in the fabric. If the fabric is too dry, if it's over dried, then this would indicate that there is a margin for us to either increase the speed of the machine, or let's say reduce the temperature, for example.
So we are now going to talk about the very exit of the machine where the fabric comes out. The exit zone of a stenter is again very similar to the exit zone of a usual open width continuous processing machine. We have devices like the static charge elimination device, which is usually installed after any process in which the fabric is made very dry, because that is when a static charge can build up and it can be very harmful. The other most important system that's provided in the fabric exit zone of any open width continuous processing machine is a batching arm or a plating mechanism. So here in this image that has appeared on the slide, you are looking at the exit section of a stenter where fabric is stored in a trolley. That's called plating. And in the second image that has appeared now on the slide, you're looking at fabric being stored on a batcher. Whether to store the fabric on a trolley, plate in a trolley, or on a batcher depends on the subsequent processes, and it's a decision that is made locally. It has no particular technical reasons, and it's not that one of the systems is better than the other. So it's really down to the processor to decide how they want to store fabric at the exit of every machine. So let's look at a quick summary of what we have covered in this lecture. The required processing conditions, that is the time, the temperature, the humidity, are maintained in the treatment chambers of a stenter. So this is where actually the process that we are required to perform takes place. We can use different heating mechanisms, and the choice depends on the cost of fuel in a given region of the world and the type of machine that you want to use. The control of air circulation is crucial in any case. So no matter you are using direct gas heating or thermic oil heating or any other form of heating, it is crucially important that you have complete control on air circulation in the stenter treatment chambers, because that is what achieves the uniformity of the process. There is a small cooling zone after the treatment chambers. From the point of view of design of the machine, it's fairly insignificant, but the role of this cooling zone is very important, because the fabric that leaves the treatment chambers has to be brought below the processing temperature so that the fabric parameters are locked in place. So this was the last lecture in the series of 4 lectures that we have covered on processing of a fabric on a stenter. Thank you for listening to these lectures, and I hope you enjoy the rest of the course.